Okay, so if this is air medium, and this is glass, so the light, part of light is moving from air to glass. Now, when the light gets to this interface, how would the deviation or the bending be like? Will it deviate away from the normal or towards the normal? Yes. If it is from air to glass, will the bending of it will be towards the normal. Okay. So what are we seeing? We are seeing that there is a change in the direction of light as the light enters the glass medium. Originally, this must be its path. Originally, this must be its path, but its path is deviated. So there's a change in its direction. So we can express refractive index by the change, the direction in one medium, the ratio of the direction in one medium to the direction in the other medium. So refractive index N or mu can be expressed as the sign of the direction the ray has in the less dense medium. So sine I over the sine of the angle of refraction, its direction in the denser medium, which is R. And this is what we call as the Snell's law. This is the Snell's law. Snell's law. So Snell's law is saying that whenever light travels from one medium to another of different densities or optical densities, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to a constant. And this constant is what we call as the refractive index of the material. And the refractive index is represented or denoted by these two symbols, either mu or this symbol. So if you are denoting refractive index, you can either use this or the other symbol. Is that okay? Are we okay? Now, refractive index can also be expressed as N or mu can also be expressed as the speed of light in air, the ratio of the speed of light in air divided by the speed of light in a medium. So mu is equal to speed of light in air or vacuum is represented by the letter C divided by the speed of light in a medium V. Because you see, even as humans, when you are running in air and then you suddenly enter into water, you realize that your speed, your speed drops, decreases. Okay, so our speed is always greater in materials with a lesser density than materials, okay, whose density is greater. So when light is traveling from maybe air into glass, within air, it will travel freely at that constant speed. But the moment the light enters into a material whose density is greater than before, then its speed will be dropped or would reduce. Please, are we okay? Are we okay?
Yes.
Yep. All right. So refractive index of a material can also be expressed as the speed of light in air, the ratio of the speed of light in air to the speed of light in a medium. Another way to represent refractive index. You see, the speed of a material, V, the speed of a material is directly proportional to its wavelength. So it means that when the speed increases or decreases, the wavelength would also increase or decrease. Okay, and so we can also express refractive index as the ratio of light, the wavelength of light in air or vacuum to the wavelength of light in a material, in a medium. Let's use medium. So the same refractive index mu can be lambda in air over lambda in a medium. So these are the three ways we are representing refractive index: sine of the ratio of their directions, the ratio of their speeds, and then the ratio of their wavelength. Please, are we okay?
Let me say there.
Hello.
Please, on the diagram, where is I and where is R?
I is here. The angle of incidence is always, just as we saw in reflection, measured from
Yes.
The normal to the incident ray, and the angle of refraction from the normal to the refracted ray. Please let me pick a call and then get back to you. I'm back now. So, and so
Miss Lydia,
hello.
Please, I have a question.
Ask your question.
Miss Lydia, please, the velocity, please, the velocity is directly proportional to wavelength. Is it a law, or like, is there anything is there a reason why it is like that?
You see, anything wave has this representation. It's a sine curve. Okay, it's like a friend of anything wavy is described as sinusoidal sine. Now, if this is like a spring. Marvelous, are you listening?
Yes, please.
This thing we are calling as a wave, which represents the form of light, is this, and it's like a spring. When a spring, okay, hits a wall, what happens? It compresses. Is that okay? It compresses.
Yes.
Now, this is what we are referring to as wavelength. The distance from this side, okay, to this side is what we are calling as a wavelength. The moment this wave hits a material that is denser, the distance between this logarithm, okay, reduces. The moment this one reduces, it means its speed has also changed because of the denser medium. So the two are related naturally. Whenever there is a change in velocity, there will be a change in wavelength, because the change in velocity happens because the body enters a denser medium. So there will be so much obstruction. When there are obstructions, the distance between the pulses, which are these things, would reduce. So they move together, right? When we get to
yes,
waves, when we get to waves, you understand wavelength and speed better, but they are related. Okay.
Okay, thank you.
All right. So we are defining refractive index by these three parameters. Now note, because velocity is directly proportional to wavelength, when we introduce an equal to sign, there's a constant, isn't it? Equal to k times lambda. And this constant of proportionality is what we refer to as the frequency f of the wave. So when we substitute frequency in place of k, we have v is equal to f lambda. Because frequency f is a constant, frequency of light or wave doesn't change from one medium into another. Okay, frequency of light is a wave, so frequency of a wave does not change from one medium into another medium because the frequency f is a constant of proportionality. Class, are we okay?
Yes, please.
So whenever wave is propagated, but okay. Hello. So whenever light travels from one medium into another, its velocity would change. And please, on condition that the two media always have different densities, their densities must not be the same. If the densities of the two media are the same, we describe the material as homogenic or homogeneous material. But whenever the densities of the two material are not the same, then when light gets into it, its path will be deviated. Okay, so whenever light travels from one medium into another medium of different densities, the speed, the direction changes. The speed also changes. When the speed changes, the wavelength would also change. But what will remain constant? Yes, what parameter will remain constant? Yes, I'm listening.
Frequency of
The frequency doesn't change because it's a constant of proportionality. Are we okay? Are we okay?
yes.
Good. Now, you see, in all these considerations, we're looking at this one, light propagated from air to glass. Okay, so the first medium is air. The second medium is glass. When we were looking at the speed of light, okay, from air into a medium. When we are looking at the wavelength, we are looking at the wavelength of light traveling from air into another medium. Now, whenever you have refraction and the first medium, okay, through which through which the light is propagated is air, we refer to the refractive index of that material as the absolute refractive index. We refer to, so when light is being propagated from air into another medium, then the refractive index of the material is described as absolute refractive index. So we talk about absolute refractive index of a material, refractive index of a material when, okay, material, when light is propagated from air into a medium. So long as the first medium remains air, we describe the refractive index of the material as absolute refractive index. Please, are we fine?
Please.
All right. So absolute refractive index is represented as, you see, the light is from air so to glass. So this is the refractive index of glass with respect to air. Okay, so the value, if it is maybe 1.5, refers to the refractive index of the second medium through the first medium. So n of what? Glass. N of glass or mu of glass through which medium? Through air. Through air. Okay. The refractive index of glass with respect to the first medium, which is air. So we can represent it like this. It can also be represented as simply N of glass or just N. Any of these three goes for absolute refractive index. So if you see N, just N or mu, it means that the first medium is air. Hello.
Please, is it 1.5 that you've written?
Oh, yes, I gave an example. The refractive index
Yes,
of
please.
glass. Okay, so if you see just N or mu, it represents absolute refractive index of a material. So here, the first material or medium must be air. Okay, now, assuming we have this situation where the first medium is glass, then the second medium is air. Light is propagated from the glass and enters into air. Will the deviation be towards the normal or away from the normal? Yes.
Away from the normal.
Good. So it will deviate away from the normal. We cannot describe this as absolute refractive index. Why? Because the first medium where the light is coming from isn't air. Please, class, are we okay?
Yes,
Class?
please.
Yes, we cannot describe this as absolute refractive index. I'm checking attendance, please. Yes.
Please, can you explain the parts where this part again?
Where?
The one
Here.
you just no.
This one.
Yes.
This one, what am I doing? The source of light is from the first medium, which is not air, but is glass. Okay. Now, because it is coming from a denser medium into a less dense medium, it will deviate, the refracted ray will be away from the normal. Okay. And this becomes the angle of refraction. R. Okay. Now what I'm saying is that if we are to describe the refractive index, this will be the refractive index of the second medium, which is what? Air. But through the first medium, which is what? Glass. Because this first medium isn't air, we cannot describe this as absolute refractive index. With absolute refractive index, the first medium or the light must be propagated from air into a second medium. That is what I mean. Is that okay?
Yes, please.
This is actually the reversed form of this one. You see, the first one is from air to glass. Now, when we reverse it, it is from glass to air. So this one is the reverse form of this other one. But we'll look at the relationship between the original and then the reverse light later on. All right. Any question? Deborah?
Mr. Dia, please, when you are writing the mu, like you are representing the absolute refractive index, but then you don't bring the A first, but G at the after the mu. Does it still represent absolute?
Absolute.
Okay.
I gave you three different. It can be mu of what? Maybe the denser medium. Here it is glass. With respect to the first medium, which is air. Once the first medium is air, it's absolute refractive index. Or mu G. This one represents the absolute refractive index of glass. Or simply mu. All these three formation represent absolute refractive index. Are we okay?
Yes,
now,
please.
Absolute refractive index of a material is always greater than 1. The absolute refractive index of a material is always greater than 1. So if we are talking the absolute refractive index of water, okay, this must be greater than 1. If the value is less, then it means it isn't absolute refractive index. Edubia?
Mr. Dia, please, does it mean that the wavelength of air is always greater than the wavelength of anything?
The wavelength
Of any medium.
of
Any
air,
medium.
the wavelength
Yes,
of air is greater than the wavelength of air itself in another medium. Okay, so your question is that the wavelength of light, it is light in air, is greater than the wavelength of light in another medium. Okay.
yes, please.
We are talking about light, the part of light entering one medium into another. So the wavelength of light in air is greater than the wavelength of light in another medium. Meaning that the speed of light in air must also be greater than the speed of light in another medium, because wavelength and speed move hand in hand. They move together. Are you okay?
Thank you, Mr. Dia.
Okay. Now, I said the absolute refractive index of water, which we can represent as this or bring that, is expected to be greater than 1. I want somebody to explain to us why is the absolute refractive index of a material always greater than 1? Yes. Can somebody explain this to us? Why it is greater than 1? Okay, Marvelous, your hand is up.
Yes, Mr. Ida, please. Because the numerator is like if you are considering speed, then we know that like speed of a substance in air is like when light is traveling in air,
the
it is
speed
3
of
times
light in air. That's what you are
in
saying.
air.
Mm-hmm.
Yes, it's 3 times 10 to the power 8. So just that, like the value is greater than 1, and if the numerator is more than 1, the denominator, if the numerator
Exactly.
is more than 1, the
Marvelous, it's
value
okay.
of
You are
the
there.
calculation
It's
will
okay. Save your English for another class, okay?
be yes.
Yes, that is it. You see, when we look at the ratio, if it's sine I on sine R, okay, once the light is traveling from air to another medium, it will be deviated, the path of light will be deviated towards the normal. So this angle is greater than this angle. So the numerator is greater than the denominator. Hence, the ratio will be greater than 1. If it's about speed, then the refractive index will be, I'm coming in. The refractive index will be the speed of light in air or vacuum over the speed of light in a medium. And here, I'm coming. And here, speed of light is greater. Okay, I'm coming. And here, the speed of light in air, C, is always greater than the speed of light in a medium. Okay, so here to the numerator is greater than the denominator. Hence, the ratio will be greater than 1. If it's about wavelength, the wavelength of light in air